Hello, my name is Sebastian. Welcome to Udacity Talks. Today is a very, very special day for me. It's going to be the best day of my year because I'm here in the temple of myth-busting together with Jamie Hyneman, who has been one of the two co-hosts of MythBusters for 14 years. Is that correct?
It's a long time, but yes.
So you've busted a lot of myths in your life.
Yeah, 14 years of daily shooting here in the shop and out on location as well. And now all that is gone, and it's just me and my toys.
Yeah.
I'm basically spending my time coming in, locking the doors, turning up the music, and
that's great.
Coming out later with who knows what.
For those of you, for the very few of you in the world who might not know what MythBuster is, it's been the world's most amazing way to bring basic science to the world. And not just as a, okay, here's the equation of physics and please memorize it, but as here's something that you believe could not happen or could happen, and we'll show you the truth about the world. Give me a favorite myth that you actually really busted that surprised people. I'm sure you have thousands.
Yeah, you know, the thing about favorites and busting, there's two things. I almost don't pay attention to whether something was busted or confirmed or not. I was only interested in what I had to do and test and what that involved. And favorites, you know, it goes all over the place. There is one story that I like to put out there, though, as what I think the most highly of, and that is the lead balloon. We built a balloon out of lead foil that was 14 feet in diameter and filled it with helium, and it flew. And the reason that was so interesting was not that it was that spectacular. It didn't involve explosives or high-speed car crashing or, you know, cannons or anything like that, but the engineering task that represented was
to make a foil that's tight enough to hold.
Well, yeah, this is a thing that this is a material that was incredibly heavy and weak. It was kind of like trying to build something out of wet toilet paper. And so to make that happen, with that size and weight of the thing, there was absolutely no room for error. And what it meant was that we had to get into our head what we were facing, how that material was going to behave in that application. We had to understand every detail with that, to the point that we, in advance of doing the experiment, we had walked through every minute of that day in advance in our heads. And it was like when we actually did it, we'd already been there. It was the closest I'll ever come to actually seeing the future.
And airtight is not enough, it has to be helium tight, which is much harder.
Helium tight, it had to hold together. This was a material that was, we had to build the thing in place. You couldn't move it once it was, you know, once it was assembled, because the material would rip at the lightest excuse. So we had to come up with, had to visualize all these contingencies and prepare for them. And for me, it's representative of something that I like best about that experience of shooting the show, that it shows the kind of, you know, what it takes to internalize a material or a process or something that you're testing. You know, if you don't get it into your head in the way that we were able to get that project into our heads, you're just looking at a pile of meaningless data on the table. Yeah. So whenever you're engineering or creating something, think about what it takes. How do you bring it into your head where you can control it?
I find this fascinating. Most of our students at Udacity are software specialists, but this shop is just amazing. I mean, it's like heaven. I mean, just seeing what kind of things you can build out of nothing is amazing. You showed me a water-formed steel plate. There's a drone over here. I guess it's a Google hat on top of it. Tell me about flight. Tell me, what are you doing with these wonderful flight machines here? Drones, helicopters, gasoline-powered, variable pitch propellers, and so on.
Well, currently I'm fascinated with the direction that I'm seeing a lot of these drones going in, and that is that as drones are getting used for different things, a lot of them involve covering larger distances. Mm-hmm. And you know, a vertical takeoff and landing craft is not the most efficient sort of an aircraft. You want to have a lifting surface with a wing, and so I'm seeing a lot of drones being what we're calling transitioning drones, where they come off in a VTOL fashion, and then they transition to horizontal flight with a wing on them. Now, the thing about that is, and we can look at what I was playing with up here, those two different states, the vertical takeoff and landing and then the horizontal flight, are asking different things out of the propellers. And because in the lifting, hovering mode, you want to have a relatively a shallow pitch that is not moving very much through the air. It's just staying stable. As you start to transition, though, and you're going forward, now you're meeting oncoming air, so the blade needs to actually either speed up a great deal, which is problematic, and there's going to be a certain limit to it, or it can steepen its pitch. And sometimes, like in a helicopter, for example, they vary the pitch on their blades, but they're using a servo or some other kind of control, though, to mechanically do that.
Same is true for small aircraft often.
Right.
Lots of them have variable pitch.
Well, I had reasoned that why not do it with a spring, because that would save mechanical complexity and weight if you could do it. And so I've set up a little test bed here with a force gauge and everything like that, and I've been playing with that, and it actually naturally seems to be adjusting to whether it's either hovering or moving forward.
That's amazing. So this spring basically keeps it flat at a high RPM, and then as you go to a lower RPM in forward flight, less energy.
Yeah, it automatically adjusts to whatever condition it's in.
Great.
And and we have to do more testing with that. In theory, you might be able to, if you have a servo, you might be able to optimize it through sensing or something a little bit more than the spring naturally does. I don't know yet, but that's the kind of thing that I've started to play with. And we're seeing a lot more of an interest in this because, interestingly, I've seen drones that are transitioning like this to do with agriculture because they're going out and want to stay in air for a long period of time.
The range is one of the big open issues for electric flight. There's
Right.
very few drones that can fly more than 40 minutes.
Right.
Because of the inefficiency of regular drones.
So this is one obvious solution for it. If you can have some sort of lifting surface. Obviously, there are problems because one of the main attractions of these the quadcopter style drones is its compactness, and if you throw a lifting surface into there, you're asking for a little more, but a little more space. But
so Jamie, you have a tank here, a Vietnam era tank. Is this going to be a toy for my son to play with?
Well,
a 9-year-old son.
We might be able to work something out. It's this is
amazing.
This is an armored, it's a variation on a M113 armored personnel carrier. These were made starting in the 60s, and this particular one isn't armored, and it was a pickup truck version of it, but it's got tank treads, it's got the same suspension and engine in it. And I can't tell you what my specific plans for this device is, because it's something that
you don't take it shopping to Whole Foods.
No. What I am doing, though, and what's required of this for the end purpose is to convert it to remote control, and so I'm in process of doing that, but I'm also doing it in an interesting way in that I'm making sure, this was something I learned a long time ago, you don't want to make something like this remote control without making it able to also be manually controlled, because if in some cases you want to have somebody behind the driver's seat, because getting it off and on a truck and doing it via remote control
so
is a
I've
bad
walked
idea.
on self-driving cars here and there, and normally what we do is we have a little electric steering booster and a torque sensor in your steering wheel, and you wire those up. But this thing has nothing electric to it except maybe the battery, I don't know.
Yeah, it has an electric starter and that's it.
So you're working with linear pneumatic actuators?
What I'm actually using servo pneumatics for it, which is the part I said about being able to make it both remote or manually controlled. With servo pneumatics, what you have is a pneumatic piston with a linear potentiometer that goes down the center of the piston shaft. So it can it can give feedback just like an electronic actuator can. The advantage with it is several things, though. It's much lighter and faster than something that is electric motor driven. It's much lighter than a hydraulic thing would be, because hydraulics, the liquid doesn't compress, so the wall thickness on those has to be massive to take any kind of surge of pressure. With pneumatics, though, the air acts as a buffer for that, so you can have relatively light and thin walls on it. And the other advantage in this particular case is that if I go ahead and put these servo pneumatic actuators in the linkage that is controlling the engine and all the other components in this, I can disengage them with a simple solenoid valve. So you hit a switch, it opens the air lines, and they just bleed if you're manually operating them. Yeah. If you want to remote control it, it's just a switch, and you're good to go. And that's something you can't do with a mechanical actuator like an electric one. You'd have to mechanically disengage it.
This is amazing. What is a giant egg, and why don't keep it in the refrigerator?
Well, this is actually one of my favorite tricks that we use when we build things here.
Oh my God.
This is a thing that we would make to vacuum form plastic. So we can, we have
wood.
Yeah, it's out of wood, and this is a particular kind of wood, though. This is, we refer to it as MDF, or I think there's a brand name Trupan, but as you can see, there are about 2-inch, 1.5 to 2-inch thick segments here. So we buy this in 4x8 sheets and then glue them together with wood glue, and press it with a pipe clamp or something like that until it cures. And then we have a massive wooden block with a very even grain on it that we can put on a wood lathe, or in this case, or use common wood shaping tools. So it's got a very even texture that you can get a smooth surface off, that is smooth enough that once we pull a sheet of plastic over it on the vacuum form machine, it has no texture that it picks up from this. There simply is no other solid material that's this inexpensive that you can do something like this with. And we use it all the time. Plastic shells that you would normally have to make by molding and casting some big thing, or machining some expensive
aluminum,
product.
Steel.
Yeah.
Quite
That's
amazing.
one of my favorite tricks.
Wow. I could spend hours here asking you questions. But let's sit down for a sec, because our students have submitted many, many interesting questions. And as we always do in Udacity Talks, we let our students speak and ask our geniuses like yourself, Jamie, great questions. But I'm intrigued. For me, this is the temple of doing something with your hand and building something interesting physical, as opposed to bits and bytes.
Well, and I just want to talk about that for a second, because we live in the real world, and for this bit about being able to internalize things, if you try to do it in a vacuum, like you're just sitting in a desk and you're in your head, it's a different. I tend to think of it, at least it's this way for me. Having a physicality allows you to pull things into your head more. So I have all this stuff, if I start to want to design things, I pull things off the shelf. I try to bend them or hit them, or cut them, or whatever it is, and sooner or later stuff starts to happen. It starts to evolve, because it's a way of bringing whatever I'm dealing with into my head instead of trying to work in a vacuum. You know what I mean?
Yeah, I do. It also means you have to have a lifetime of experience with different materials and manipulate things, and heat and moisture and all these wonderful things that come together in the physical world.
Well, and that experience builds a foundation, which I like to make the point of. It allows me to make intuitive leaps into areas that I have no direct experience with. So this is something that, again, if you're working in a vacuum, you may come up with ideas, but they may not be useful. They may not be practical to actually put into work. having that foundation, even though I've never done something before, I have some wherewithal to judge whether it's actually a reasonable thing to do or not. And that's what is beautiful about having, and I'm an advocate for that. I think, I forget who it was, Asimov or somebody, that said specialization is for insects. And you know.
None of the degrees are for insects. I take it. Okay.
well, and I mean, like, there's a need for specialization. Actually, it allows you to.
Important.
Well, it allows you to make a certain penetration on a linear path that is important. But I want to say that, so I'm not dispelling the need for doing some of these things where you've got somebody that knows a lot about one specific thing and has invested a lot of time on that. But what that also means, though, is if that person who has specialized in that thing runs into a speed bump or some kind of a problem, they may not have the wherewithal to figure their way around it because they don't have this broad foundation. So specialization is fine, but do other things as well, have a foundation. That's been the trend, the sort of the trajectory on my career, was to build this broad range of experience, and then now when I want to go in a specific direction and really you know, penetrate that deeply, I can do that, but I can also navigate my way around an obstacle at the same time.
Boy, I would love to be a student or the fly in the wall for half a year, seeing how you build things that can't be built.
Somehow I don't think you'll need to.
No, I could learn so much from you, trust me.
Well, and
I learned so much today. How to use your standard drill and turn it into a robotic arm for a humanoid robot. It's something I haven't seen before.
Well.
Very, very smart.
And vice versa. I'm sure I'm sure you could teach me a thing or two as well.
Let's see. So we are launching and now have a robotics nano degree, and sadly it's more software focused. The reason is we can much easier bring it into the world as a software focused than in a hardware focused, but there's some hardware components. But Adam wants to know, one of our students, what is the most compelling area of robotics for you today? Is it flying vehicles? Is it tanks?
Well, I like to think of robotics as not something where, okay, so you've got this thing that's a robot and it can do things by itself. I like to think of robotics and the way that I would like to see them working with us as an extension of ourselves. And you know, there are times where simple remote control, for example, is just as good or better because you're able to interact with that thing, but it's an extension of your abilities and it enhances your abilities. Like an exoskeleton, for example, might be one of those things. And
that's be great to have, by the way.
Yeah, well,
fun to be like 1/10 times as fast.
Yeah, and that for me is more interesting than having this little thing that can run around by itself and do something. I want to do the thing. I just want to do it better or faster or stronger.
You believe as a voice as human augmentation, from the early farming equipment to today's teleoperated robots that might be on space stations or similar.
Yeah, I mean, and I think down the road, like as far as robotics as well, you know, I don't find it particularly appealing to have a scenario where I can just stay in my armchair and watch TV all the time because the robots are doing all the work and we don't have to. You know, I want to think of the future scenario with robots for me is more of something that allows us to do things that we by ourselves couldn't do as well or do as much of. And so that's my particular take on it. You know, people ask about, you know, what's the future of robotics and everything, and I'd like to encourage that sort of an approach where robotics is for extending our capabilities.
I like what you say, because I think technology is for extending our capabilities and has in the history of humanity.
Yeah.
So when people talk about artificial intelligence, I believe it's about extending us, not replacing us.
Exactly.
Nick asked a question that I find really interesting. When you, Jamie, start a new project, how you take the problem at hand and start working towards a solution? Do you start with experimenting, sketching something out, doing math simulations, thinking and jogging on the beach? Like what's something you've never done before, like exploding a big tank or something? How go about it?
Well, one of the things that I haven't heard anybody really go here, I haven't heard anybody say this before, but one of the things that I've always thought is that the mind and the body really aren't so separate. You tend to think on the face of it that, okay, so I'm going to invent or make this thing, I've got some problem that I need to solve or something I need to create. And so you go in your head and you figure it out. Well, the first thing I do is I get on a treadmill. And because I find that mind-body connection is really important, and there's evidence to back that up. The increased oxygenation levels and chemicals, hormones, and things that are going. And when you think about it, also and this is speculation, but when are the times that we are, as humans, that we have evolved to need our brains the most? Well, those are also times that we've needed our bodies the most. When we're hunting, when we're mating, when we're at fear for our lives, both things are going at full performance in those situations. So they didn't evolve separately. So this idea of sitting at a desk to figure something out doesn't work for me. I'll do that and everything. There's certain things that are not practical to do while you're running on a treadmill. Personally, I'll set it to a steep setting, and I get to a comfortable aerobic sort of. I get in a butter zone with that, and I find that it's like hitting a switch for me. The difference between being able to think while I'm physically active versus thinking when I'm stationary.
I'm just picturing you on top of this robot called treadmill now, inventing new robots.
Well, it could be. So that's one of the things that I do, and I think the other thing that goes along with this, which is important, is that because it's impractical to be typing on a keyboard and doing CAD work or something like that while you're walking or running, I've been forced in this situation to visualize the thing that I'm working on in my head and do the design work simply in the head. And so I've refined that process to where I have a specific space that I create that's like a shop. And I bring things into it, and I intentionally force myself to visualize details in the room that are maybe even irrelevant to the project at hand, but it starts to build an environment where there are attachment points in my brain that are created by that room and by putting things in that room. And now we're in a situation where it's basically like I've got this CAD program in my head that I can use and I can manipulate, and it's doing things automatically. It's making connections that are subconscious because of that. Things that where I haven't figured out how to do something, but I put all the relevant elements there in the head, and then there it is.
Nice.
It does it by itself because you're making all those little mental, the neurons are starting to link up. Does that make any sense at all?
I am very strongly suspect I'm talking to a true genius here, to be honest.
Well.
And I think all the important discoveries in the world don't come from CAD tools, but they come from moments where things are simulated the way you're describing them, which is great. Do you experiment much when you do this?
Oh, yeah.
Iterate.
Well, the other, there's another thing that is interesting that I've learned, and I have to say part of this, me talking about this in this way is a direct result of having to learn how to express myself on Mythbusters, because everything we did, we had to talk about, and we also got all of this attention for putting science out there, and asked a lot of people asking questions. Why did this occur? Well, and so I've learned how to articulate it, but one of the things that I started articulating with this, that I described this scenario where once these things get in your head and the neurons start to make those connections automatically, I find that when I start to apply myself to a problem, whether I'm on the treadmill or in some other environment, I describe this as pushing. It's like, in a simple scenario, as an example, is that say you're in a room and there's a refrigerator there that you've got to move across the room. And you don't know whether it's too big, you're too light, or not strong enough, or what the floor texture is. So what do? You go up and you push on it. Well, okay, so it doesn't move. What are you going to do then? Well, maybe you grab one corner and try and see if you can get it purchased somehow, rotate it, leverage somehow. You apply yourself, and you might well find that, the thing starts to rotate, and then now you're rotating it across the floor, because that seems to be the thing that's actually working. And so I find that when I have something that I'm trying to do, a task that I'm trying to accomplish and figure out, just simply getting in there and pushing on it in that way it starts to make things happen. It allows these neurons to start to connect. You start to see evidence or a hint that this particular feature is working, and so you build on that, and you apply more leverage. You start to build an environment and an understanding of what you're dealing with, simply by applying yourself and taking note of the evidence that is presented, and then you continue. And I find, that, and we saw this all the time on MythBusters. We would come into something that we had no experience whatsoever with, had not a clue how we were going to deal with it, but we simply came in and started to push and poke at it, and things would get teased out, and we'd find a trail that we would follow, nice. and then there you go, and it's done.
I think you just described to me how to build a successful startup company. People here in Silicon Valley often ask me the question, how do you succeed in companies? And we have this picture of throwing spaghetti at the wall until it finally sticks. And that's the same as pushing the refrigerator box to the kitchen until it finally moves. And it's very painful in the beginning, because often people have an expectation you have to get it right in the first shot, but I think the process is much more important.
Well, and it's exciting when things actually start to move.
When the spaghetti really is on the wall and hangs there.
Yeah, then you put something that didn't exist before together, and that's creation. I noticed you're looking at some questions for reference, and I had looked these over as well. This sort of points out this bit about creativity in engineering, and it's incredibly creative. That whole process, like what can be more creative than this sort of thing where you're trying to problem solve and something comes into life that didn't exist before. And it can be something that's useful, something that is that maybe you don't know, that has yet to find a use, but it's engineering and creating these things, experiencing that process. It's just so incredibly thrilling and creative.
We really try to distill in all of our students that failure is an option. It's great, actually. You don't really fail. You do something. You fail if you don't learn, but if you do learn, then you do something and you learn from it, and you know more. You never make the same mistake again. And even it looks like a failure might end up to be a big success. There's a question from a guy named Antonio, which is fun. Antonio says he's always been fascinated by the idea of machines that repair and replicate themselves. How far can you build one of those? How far are we?
Well, that one is pretty easy for me to parse out when just in a simple way. It's like, as a builder, when I'm fabricating something, I've got to like if it's a machine, because we're talking about a machine that can replicate itself. Well, when I make a machine, or repair a machine, or evolve a machine, I go to the lathe, I go to the drill press, I go to the milling machine, I go to the welder, I get metal stock.
It's cool to have a robot do this for you.
I've got drawers and drawers of this size of bolt and nut, and that size of bolt and nut, and a bushing and a bearing. So how are you going to have a machine that, is it a machine that exists in a shop like this that can go navigate through all of those drawers and pull out those?
I would be impressed if you had a robot that could build itself in this shop.
Well,
and
I think that
components here.
For me, that's a ways off. Like what this image of this robot that can fix itself and replicate itself, it sort of means that it's got the wherewithal to do these things, and it's not gonna. It doesn't imply that there's a shop there. It implies that it's able to.
It's nature. It's saying
well,
ions.
Yeah, I think that's. I think personally that's pie in the sky, and that the only thing that that is coming from is, okay, so now you've got 3D printers, and you could have a robot with its own 3D printer that can sit there and, patch a hole or build another little structure. But there's a lot more as the point to some kind of a complicated machine that's able to build something. There's a lot more than simply laying down a little, a bump or a flange or something else or a patch.
Yeah. Cameron asking a question, so I find this very interesting for students. What are you currently learning? What skill, technique, or methodology are you currently a novice and you want to improve?
There's so many things. I need to, to put in perspective what I've done here, I'm reasonably versatile with most everything in this shop, and that's one reason that I was able to make a business out of it. If I would estimate the cost of a job and so on, I could build that thing myself, so I knew how much time it was going to take to build it, and therefore how much to charge for it, and what was going to be the problems with this or that process that was involved. But there were some areas which are more in the areas that you guys have expertise in, programming, doing things with 3D printers and CNCs. Those were specialized things that I would have employees deal with. And I know enough about how those work to be able to estimate them and deal with them as a business owner. But as far as me coming in here and following through the whole process, I have a ways to go.
Well, we'd be happy to give you a
rebate
on another degree in the software field.
Yeah, I was going to say, I'm definitely going to enroll in Udacity and take some of your courses.
One last question I want to ask you. It's kind of a tricky question, but what would you like to invent next that hasn't been invented yet? What are you itching to solve?
Well, at any given time, I've got close to a couple dozen different things that like that I would like to
Give an example.
Let's see. I've got I showed you some special shoes that I have in the other room. I can't talk about all the details of those, but that leads to one of my favorite things is this concept of like an exoskeleton or things that robotic things that extend the capacity,
so
the
it makes
reach.
you run faster and longer and carry heavier payloads and all these things.
Right. Now, things like exoskeletons, as an example, and this is one of the areas that I'm that my particular background equips me to deal with. And because I've experimented some with this stuff. If you're putting something on a human being that is to work with them and integrate with them, it effectively has to be as fluid as that person. Even something as simple as a motor enhanced or spring enhanced knee joint. It's not like there's an axle like the axle on the forks of your bicycle that will line up with wherever that is on your knee. But that's what you need typically to have a spring there or a motor there to turn a gear or something that enhances that joint. And I've gone through this whole process. If I were to try and carry that through the whole body, from the ground through my ankle, through my knee, through my hips, through my shoulders and arms and things like that, every error in that lineup of those axles, because you've got your knee is this sort of floating thing and there's all this fluid and flesh around it, and everything else is the same way. there are errors with those linkages. Every one of those gets amplified by the time you get to the,
so you could really hurt yourself.
Yeah, so this is an incredible challenge to have a machine that integrates with the human body. And that's one of the reasons that somebody like me should look carefully at that, because I have such a wide range of materials and processes that I'm familiar with in my toolkit. And so I'll probably be, well, I am looking into those kinds of things. I like this idea of robotics, as I said, not just as a separate thing, but something that is integrated, some way of enhancing what I can do. But I'm very familiar, for the reasons that I talked about, that it's not a trivial thing. You think, oh, I'll just mount this in here and here, but you try it, and you try to start strapping this stuff on, and it just, it's a really tough challenge.
Jamie, I find your work unbelievably exciting, and of course I've watched Mythbusters many, many times, as I'm sure many of our students have. It's been a privilege and pleasure to be spending a morning in your wonderful shop and talking to you and learning from the master himself. Thanks so much for being such a great inspiration for us for such a long time in this country and around the world.
Well, thank you. I appreciate it. Thanks for spending the time with me.
This is Udacity Talks. It's been a real pleasure here in San Francisco, reporting from one of the craziest places on earth, the temple of anything that blows up and can be built and can fly and crawl and help you move faster. I wish we could invite all our students to come here and spend a year here and learn from the master themselves. Unfortunately, don't fit into this room. But take out another degree in robotics, and hopefully you can do little steps along the great steps that this wonderful master has been doing, taking all his life. Thank you.
Udacity is great.
Thank you. So this is actually not a myth, right? Don't bust that myth, please.